An ozone generator. A shady ozone generator from eBay that doesn't quite comply with British, or indeed worldwide electrical standards for a slight shock risk. But best of all, it's a faulty ozone generator. So let's see if we can fix it. And then either way, we'll take it to bits, reverse engineer it, and draw out the schematic of what's inside. So this came from one of the Chinese warehouses in the UK. And is described as 220 volt, 24 gram ozone generator, integrated plate, air purifier, ozonizer, sterilizer. It cost £16, which is cheap. That was including shipping. And it says, this ozone generator is portable, easy for professional DIY use. Couple of issues with that, particularly the picture of somebody putting their hands either side of it, because it's nasty. It's nasty. So this came, let's see if I can find the box. It came in this box, and you can see there's not really much in the way of room. There was no packaging whatsoever. So when it arrived and I connected it up, it immediately, instead of doing this sort of thing that these ozone generators do, and it makes a sort of noise, and you see the purple glow surrounding these black conductive lines. Instead of that, it kind of made a fizzing, arcing noise, and I could see a spark going between the plates here. And if you look, let's zoom down on this. If you look at this end, you may see that the ceramic is cracked. The insulation has failed, and therefore, instead of actually creating the corona, it was just arcing through the plate at that point onto the plate at the bottom via this metal separator. So let's see if we can fix that. And the way I'm thinking of fixing that is just to disconnect these plates and see what... Hold on, let's unscrew that. Let us unscrew this. Is this a good idea? No. Am I going to do it anyway? Yes. So, I shall explain how this works in a moment. Regulars to the channel will already know how it works. Those who are not regular to the channel will probably benefit from that knowledge. So we've got little springs as spacers, which is an interesting approach. And they will also couple the metal plates together, I suppose. But the metal plates are active. If you touch this while it's running, you would potentially get an arc to your hand. I'm not sure what the circuitry is like inside. The bottom plate in this one looks okay, but tell you what, let's disconnect the top completely. So these are wired in parallel. So let's chop that. And we'll chop that under there. And remove that. And put a couple of these screws back in. Do I even need to do that? Probably. What's the rest of the plate like? This is individual metal plates. These are two separate plates. It looks relatively intact. Let's see if it works now. So I shall put a screw in each corner in a sort of half-assed reassembly methodology, just to hold it together, and then we'll power it up and see what happens, if it continues to arc or if it goes bang or whatever these things do. It's worth mentioning that I've already assessed that the voltage it operates at is probably in the region of about 4,000 volts. Let's see if these plates do separate. Not easily. I thought, oh, they do. Are they held together with anything? Oh, they're kind of glued together at the end. That's why it wasn't separating. Okay, interesting. Right, tell you what, let's get the hoppy up. And we'll see what sort of stuff this puts out. That's a kind of squint there as well. So let's stuff these wires into the hoppy and see if this now operates, now that that sort of arcing short circuit is out of the way. And this will also give us an indication of power. This might just arc across loudly. It's making fuzzing, buzzing noises. The hoppy says 136 watts. That's a lot. I can see the purple glow. Let me just take the exposure off. There's the purple glow. I can smell the ozone. It is actually overpowering ozone. So power factor 0.9, that's good. Keep my fingers away from that. 155 watts is ridiculous. That is immense. That's drawing over half an amp. Right, lights coming back, shield your eyes. Oh, the place is absolutely stinking. What's the temperature of this now? Is this going to hold a charge? Boop. Right, okay. That's pretty hot. That was dissipating so much power that that really should be... This module should be mounted in an enclosure with a fan. Oh, that is just overpowering with ozone. Right, tell you what, I shall just suffer it. It's just overpowering. Right, tell you what. No, actually, I'm going to just get out of this area for a moment. I'll be back in a moment. 1 moment, please. Okay, that's most of the ozone cleared out the area. I don't mind ozone, but not in huge quantities. And this thing produces huge quantities of ozone. This plate appears to have survived. This one, when I attempt to take it apart, it's clear that that's where the crack had been, basically a pressure being applied to the top of this cable in shipping, and it had cracked this because there's no support there, because that is where there's a little bond from the back of this plate with a solder connection onto the back of that plate, because these circuit boards have a metallized coating deposited on the back. And then on the top, they've got this outline printed. And a lot of the energy, I'm guessing, would be coupled capacitively between the two of them. It's not going to be super efficient, but still a very good way of producing a lot of ozone. I'm surprised at the power. That was ridiculously high power. The top layer appears to be a conductive ink. Now, how did they solder onto that? I have cleared some of the stuff away. I feel the need to get the soldering iron on and explore that. So the soldering iron is now on, and we shall explore it. But they've got a conductive ink that has the black sort of layer, but then they've put, this is the active corona discharge area. They've then put a sort of coating over that, almost like it feels Teflon-y, which would make sense because it is fairly resilient to, ozone. So what was happening there when this was shorting out, because these two assemblies were in parallel and it needs that voltage to actually arc across and create the corona discharge, because it was effectively shorting out one plate, all the energy was being arced across in here. Yeah, you can see the burn mark there. Onto the back plate, and that basically shorted out the unit. It clamped the voltage down and stopped the rest of the unit generating ozone. Right, let's try and melt that solder connection and see what's underneath this. Is the soldering iron up to temperature yet? I shall wet it with some fresh solder. It is just barely up to temperature, so I may be a bit premature here, but it's not a high mass thing, so I'll just I shall see if we get any joy. It should, hopefully, the silicon on it is actually meddling with my ability to melt the solder. Hold on, I'm going to have to scrape that off a little bit more. I shall get a knife and scrape it off. On the bottom, it's a fairly straightforward. It's a solid coating on the bottom, a metallic coating that looks quite easy to solder onto. The sort of thing you might find printed onto solar panels for the connection. But the top here, I'm not sure what the black stuff is. Can it be scratched? It's very hard. Almost as hard as ceramic itself. That is a very strong coating. I'm not sure what that is. Let's have another go at melting this. The high voltage wire shouldn't be a terribly... This might be a specialist solder. Hold on. I shall try and flow some solder directly into it. It may be a high temperature solder, or might even not be solder. There it goes. Let's scrape that off. Oh, scrape the whole lot off. There's a separate coating there. I think maybe they've printed a metal coating on, but then put the black stuff over the top of the conductive coating, just as a maybe protection, because ozone is extremely aggressive. It's a mega oxidizer, and it will damage electrodes in short measure. These have probably been optimized over a long period of time. Right, tell you what, here comes the theory. So I'm just going to, no, I'm not going to tame it down, that looks fine, but I will focus down onto that just to make it a bit sharper. Here is the theory. Regulars to the channel will know this. Anybody who's new to ozone will not know this in the corona discharge method. After this, we'll open this unit up and we'll take it apart completely and see how it works. So if you get a high voltage transformer and you bring it out to two electrodes and there's nothing in between them and they're close enough, you'll end up with a spark jumping between them. If you take the same high voltage transformer and you get the same electrodes, but you put an insulator between them, in this case it's the ceramic material, the spark can't jump straight across. So what you end up with is it capacitively couples the energy, so lots of tiny little sparks occur and it creates a corona discharge, that purple glow. It's just basically it's the flow of electrons backwards and forwards at the AC. And these units often use high frequency transformers. The earliest ozone generators just used low voltage 50 or 60 hertz transformers, but it's much more efficient. You get much more output from high voltage, in this case ridiculously high output. So what they do here is they've got this ceramic layer and they print a pattern of fingers onto that and then connect onto it. And what happens is that if you were to see that from the side with the raised electrode and then the conductive layer at the back, you'd see a corona discharge fingering out from the side there. And what that results in, you get a glow that follows the outline of these tracks. And the higher the voltage goes, the more they spread out until you get to the point that if you go too high, the ceramic, even though ceramic's got a really high voltage rating, it can break down. If that happens, you'll suddenly end up a crack. It'll pierce it and it'll start glowing and burning at that point. I had that when I did it with glass. So the corona discharge, if an oxygen molecule, which is two atoms of oxygen bound together, that's why it's called O2, if it passes through that corona discharge, as it passes through, it breaks the bond between those. So you end up with two separate oxygen atoms, and they can either be on their own, just an individual atom, or sometimes they can actually rejoin as three atoms of oxygen, and that becomes O3, which is ozone. Ozone is named ozone because I think it's Greek for smell. It indicates a ridiculously strong smell. It only takes pretty much 0.1 part per million to smell ozone strongly. But because this is unstable, because it wants to go back to just plain old O2, it wants rid of one of those atoms of oxygen. So if it hits something like a virus or a surface, it tries to get rid of that oxygen onto that, and it oxidizes the surface. In the case of a virus or bacteria or odors, it will damage them, it will break them down, it will get rid of smells. It's almost like airborne bleach. And in the case of certain materials like rubber, it will perish them, it will damage them. So you have to be careful in its use. I'm pro-ozone. I am fine with ozone at natural levels, which is about 0.04 parts per million, roughly. Let's focus back onto this, and let's open this up. I'm inclined to say I kind of want to cut this. Tell you what, let's take this thing off, just to make this more convenient to work on. Because I did get in touch with the seller. They did that thing where they say, I have contacted my supervisor and he authorised me to give you 50% refund. Now, well, 50% refund isn't very good for something that is making loud arcing noises and not doing its original job. And they grudgingly then sent the full refund. I don't normally ask for refunds like that. If I've ordered something that is deliberately shady, I just accept that, I deliberately ordered something shady. I've got a confession. I know what's in this because I took the back cover off this on a live stream recently when we were talking about it. So I know that there's two transistors attached onto the back. And I know that there's this feedback core and the capacitor arrangement that looks it's very different to the tube-based ozone generator. This one looks like it's very similar to the ballast you'd find in a compact fluorescent lamp, but it's got two cores going over into this section which is potted with resin. I can see the multiple windings of the high voltage transformer there, and I can see where they filled it up with quartz chips, as they often do, just to save on resin. It makes it kind of fire resistant to a degree as well, I suppose, but it also cuts down the amount of resin they use. So now, I kind of want that circuit board out the bottom of that. Am I going to be able to get that out easily? Let's just flex it slightly. Let's get my screwdriver down and just try and lever up in that. Oh, it's moving, it's moving. It is moving. Oh, it's not potted in resin on this side, it's silicon. Well, that's nice, that's what we want. Should I be making sure this is discharged? Possibly. Those capacitors, the red ones, probably could impart a nasty surprise. Let's short them out. Let's short them out with a pair of long-nose pliers. I don't think they'll be holding a charge. I shall cautiously hold this end. No crack there. No crack there. Right. Okay. Right. I think it's time to reverse engineer this, and we shall see what we can see. One moment, please. Are you sitting comfortably? Then I shall begin. So I'll just go over the basics of the components on here, then I'll show you the back of the circuit board, and then we'll look at the reverse engineered schematic. Fuse, metal oxide varistor to protect against voltage spikes, a bridge rectifier based on discrete diodes, not 1N4007s this time, but 1N5399, which is a 1.5 amp version. I think they've just gone for the slightly higher current. We have the two main red capacitors at the back there that form a capacitive bridge between the positive and negative side and allow this winding and the primary of the transformer to be alternated between positive and negative, so it is feeding this with AC effectively. We have the sense core here, which is used to detect the current that's flowing through that, the primary of the main transformer, and provide feedback through two auxiliary windings onto the transistors, which are actually not visible here because they're actually in flying leads off the board. Other things worthy of note: this diac type component and this capacitor that it's connected to, which is used as the start circuit for this. Okay, so that's the component side. Not terribly clear because some components are hidden from view. Here is the underside of the circuit board with some of those things drawn in, but I won't even linger on that. I'll show you. Here are the connections going out to the two NPN transistors, which incidentally, I should have noted that in this drawing. I shall note this in this drawing. Let's move this into position. Let's go a little bit closer. I won't tame it down because that looks pretty good at that, quite frankly. These two transistors are what I believe to be FJP13009. I think they were labelled, hold on, where are they? They were labelled J13009-2. Seems to be a fairly standard transistor used in this type of power supply. So here's what happens. Live and neutral come in. It goes through a fuse, and then there's a metal oxide varistor there to protect against transients, possibly in both directions, and then the discrete bridge rectifier. I've just drawn it as my usual lazy rectifier. That produces a positive rail and a negative rail, but it should be mentioned there, other than these capacitors here, there is no actual smoothing, and the circuitry will effectively, it will oscillate on each half of the sine wave. That's why the power factor was actually surprisingly good. It's very reminiscent, the circuitry is extremely reminiscent of the old-fashioned electronic halogen lamp drivers before the era of LED lamps. There are two transistors. These are the ones that are off-board for cooling, and they bridge from positive to negative. One of the most common failure modes is when things get too hot, transistors start turning on, and then they bridge the positive and negative, and it goes bang, basically. But the idea is that you've got the primary coil, you've got the sense coil here, and as each transistor alternates on and off, current will effectively flow from one capacitor will be charged and the other one will effectively be discharged or charged the opposite polarity when each transistor turns on. So there's always current flowing backwards and forwards in these transistors, and therefore current flowing backwards and forwards through the primary of the transformer. The transformer itself, the stuff that's potted in under here, has a primary winding of less than 2 ohms and a secondary winding of about 100 ohms. It's really quite a high power little transformer at high voltage. But its primary, the only bit I've shown here, that I've drawn the transformer over there, but this is the primary of it here in series, this little feedback transformer, this core here, which I've labelled with orange for each of the sections of the windings connected to it. So as current flows, say for instance current is flowing to the 0 volt rail via this transistor, because this transistor is turned on, it will be As the current flows through that, this winding will effectively be turning that transistor off, but it will be turning this transistor on. And then when this capacitors are fully charged and discharged, then this transistor starts turning off, the current through the primary starts collapsing, and then it starts flowing in reverse, and that then turns this transistor on. And likewise, it turns that transistor off. So it's just basically alternately switching between those transistors. And normally with transistors between two positive rail, you'd have a PNP transistor. But in this instance, because it effectively has its own transformer coupled supply to its base here from the emitter, you can use standard NPN transistors for both of them. That's a common thing as well. So there is one small other aspect to the circuitry. Now, a couple of things. There's a 2.2 nanofarad across that capacitor and a diode across this 2.2 nanofarad capacitor across this transistor and a diode across this transistor. I think they might largely be to protect against high frequency, high voltage capacitive coupling coming back from the secondary to ground via the primary and creating rogue voltages that would make this circuitry go bang. I think I wonder if they've patched these in as things to try and prevent that, because dealing with the high voltage transformers is always a bit of a nightmare, because when one side gets referenced to ground, you get capacitive coupling that can be quite high voltage, and it wants to find its way back to ground and finds its way through the circuitry. Other things worthy of note are 1, 2, 3, 4 components here. These are important because there's no smoothing, it needs to start oscillating. So to start oscillating, it works almost like a dimmer. It's got a diac to the base of this transistor. And when this, on each half cycle, it's full wave rectified. So if that's a 0 volt rail, it's actually bouncing up and down like that. On each half cycle, round about there, this resistor will have charged that capacitor very low value up to the point that it's exceeded the forward voltage of this diac, and that then triggers this transistor. When the transistor turns on, though, it will effectively, via this diode here, it will keep that capacitor discharged. So when this is oscillating at high speed, it's effectively continually discharging that, because otherwise this capacitor would want to charge up and then trigger it again. And they don't want a trigger to this, particularly when that transistor is turned on. It could be quite violent. So that diode there, which is possibly a high speed diode, just repeatedly discharges this capacitor, so it can't do it more than once. But when it does trigger at the beginning of the sine wave, it then runs across that full sine wave, just self-oscillating until it peters out at the end. And then the start of the next half wave, it will trigger again, and then it will start running as a series of spikes across that. And that is fundamentally it. The high current alternating positive and negative pulses through the primary induce the high voltage in the secondary, which then goes across that insulated plate, the ceramic plate, and that creates the corona discharge in that area, and that creates the ozone. I'm guessing that a similar circuit would be used with neon tubes, but if it was used with neon tubes, I would expect a capacitor to be in series that to limit the current in each half cycle, and that would effectively help it self-regulate. Maybe this is what's in little neon power supplies. I have one here. I should at some point depot it, because it is fully potted in resin. But that is more or less it. It's a very simple circuit, deliberately a very simple circuit, but it achieves the desired result of creating a high voltage, high frequency supply with relatively good efficiency, which is then used to create tons of ozone from these ceramic ozone plates. Worth mentioning that they've used various other materials for ozone plates in the past. They've used glass, mica and ceramic. The reason they tend to use ceramic these days is because it's much more reliable. It's got a higher voltage rating than either mica or glass. The mica and glass ones tend to puncture through, and I've had that when I've been doing experiments and I've pushed them too far, and suddenly the glass does break through. You see an orange flame coming out where it broke through, because it's basically liberating, it's heating the glass up to a molten temperature, that spark going through it, and it's liberating the sodium from the glass. But then it usually at that point, once it's heated it up, the thermal stresses cause it to crack from that point. And then you've got a little arc on your hands, a little flaming arc, which is also potentially, well, I know it's a potentially failure mode, because I had it with this one when the ceramic was supplied broken, and it just arced straight across with a very, very hot arc, like a sort of igniter arc. But there we go. Very interesting. Much simpler circuitry than I was expecting, but also I'm impressed that it is sort of high frequency AC it's putting out. It's not that horrible pulsed thyristor one that just basically on each half wave it charged capacitor up and then dumped it once it had reached a certain threshold. This one is much more efficient and more practical. Probably is based on the neon technology. But there we go. Interesting stuff. Well worth taking apart.